Good morning, everyone. Today I'm representing my research draft titled Controlling Dynamic Recrystallization and Surface Quality in Industrial Hot Rolling of High Strength Low Alloy Steels, a multi-scale model based microstructure mechanical properties, of course, and applications framework. My name is Robin Islam Chaudhry Robin, and I'm also from mechanical engineering, doing Master of Engineering in Wollongong University. To begin with this topic, let me show you some of the table of contents are there. It's like in the draft, and there will be some list of abbreviations like HSLA was that, this and that. So if you can read it, you will understand. So let's back to the topic. To begin with this topic, this is important. Like the topic, because high strength low alloy steels or HSLA steels are widely used in infrastructure, transport, etc. places. These steels are valued because they provide high strength, good toughness, relatively low weight. However, their final performance does not depend only on their chemical composition. It strongly depends on what happens to their internal structure during hot rolling. And what is hot rolling? Hot rolling is like manufacturing process where steel is heated and passed through rollers to reduce its thickness and shape it into a useful product. And during this process, the steel experiences high temperature and high pressure also, and it is like in repeated deformation. One of the most important microstructural process during hot rolling is like dynamic recrystallization, or you can say it's DRX. In simple terms, like DRX is the formation of new strain-free grains while the steel is being deformed at very high temperature. And if this DRX is well controlled, the steel can have a refined and uniform microstructure. If it is poorly controlled, the steel may have uneven grain size and inconsistent mechanical properties. And at the same time, another major issue is like in hot rolling is a surface quality, right? So when steel is heated, oxide scale forms on the surface. During rolling, this oxide layer may crack, break, or any kind of things can happen, like it will be uneven, so this can create surface defects. So therefore the research problem is not only about improving the internal microstructure but also controlling the surface quality, right? Okay, so in this introduction part, I explained that industrial hot rolling is very difficult to control because the conditions change very rapidly, like temperature, strain rate, rolling speed, alloy chemistry, different things that depends on this, it's too much. So existing model often study these issues, like different journals, papers I went through, that industry needs a combined system that can predict both microstructure and surface defects in real time. Moving to my literature review, the first key area is HSLA steels and hot rolling. Okay, so the literature shows that microalloying elements such as niobium, titanium, vanadium are important because they form small precipitates. These precipitates interact with grain boundaries, dislocations, which can delay recrystallization and refine grain size. However, many studies are based on laboratory tests which do not fully represent real industrial rolling conditions. The second key area is dynamic recrystallization. Earlier research explains that DRX depends on temperature, strain rate, and deformation conditions. Some models used general Holloman parameter to identify whether DRX will occur or not. This is very useful, but it is often too simple to capture complex industrial conditions, especially in multi-pass rolling. And my third area is modeling approaches. Mean field mean field models are fast and useful for industrial calculation, but they only predict average behavior. They cannot show detailed grain morphology. Full field models such as cellular automata or crystal plasticity finite element models are more accurate because they show microstructure in great details. However, they are computationally expensive, so they are difficult to use in real-time industrial control. The fourth area is machine learning. You understand? So, machine learning can make predictions quickly and can identify patterns in large data sets. Some studies use machine learning to, predict DRX rolling force, step shape, etc., etc. The fifth area can be like surface quality and oxide scale behavior. The literature shows that oxide cracking depends on temperature, scale thickness, oxide composition, and ductile brittle behavior of FeO, that's iron oxide. However, many oxide scale studies use simplified laboratory conditions and do not fully capture multi-pass industrial rolling or descaling sequence. So, from this literature review, several research gaps become clear. First, there is no integrated framework that predicts both DRX and oxide scale behavior together. Second, accurate full-field models are too slow for real-time use, right? So, yeah. And third is machine learning models are fast but often lack physical grounding. Fourth, microalloying and precipitation effects are not fully included in many DRS models. So finally, surface quality models are not well connected with microstructure models. Okay, so this gap lead directly to my research question: how can dynamic recrystallization and oxide scale behavior in HSLA steels be predicted more accurately under industrial hot rolling conditions using a hybrid modeling framework? Okay, so yeah, so how can okay, the aim is to like develop a model that can predict DRX evolution, predict oxide scale cracking risk, and operate fast enough for real-time patrol. Now I'll describe my research design. Okay, so this study uses an experimental and computational hybrid design. It is experimental because different models are tested and compared under controlled conditions. It is computational because the main investigation is carried out through modeling, simulation, and machine learning rather than direct industrial mill trials. Okay, so this design has like two main. Okay, where is that? Yeah, this design has two main comparison groups. The control group is the mechanistic DRX, yeah, okay, the model alone. This represents the baseline model. The experimental group is the hybrid model, which combines DRX modeling, machine learning, oxide scale prediction. Yeah, by comparing these two groups, the study can evaluate whether the hybrid model improves accuracy, speed, and prediction of surface quality. Okay, so the data will come from published DRS datasets already, oxide scale studies, simulated rolling schedules. These include datasets related to temperature, stream rate, microalloying effects, oxide scale thickness, and rolling schedules. The model will first be like benchmarked against them, and then the hybrid model will be evaluated to see whether it improves prediction under more realistic hot rolling conditions. You can understand, right? The main advantages of this design is that it combines the strength of different methods. Physical models provide metallurgical meaning and interpretability. Machine learning provides like speed, adaptability. Thermal mechanical modeling helps connect rolling conditions with oxide scale behavior. Together, this makes the framework more useful than using one method alone. Another advantage is that the design directly addresses the gaps and found in the literature. It does not only focus on internal grain refinement, and it does not only focus on surface defects. Okay, instead it connects both because both are influenced by the same rolling temperature, strain, and deformation history. However, the design is also has limitations. The most important limitation is that the study does not use direct real-time industrial mill data. This means the model may still need further validation before full industrial application. Another limitation is that full field models are excluded because they are too computationally expensive. Also, oxide scale behavior is simplified, and machine learning performance depends on quality and diversity of available datasets. In conclusion, this research is important because modern steel manufacturing needs stronger, lighter, and more reliable steels with fewer defects. HSLA steel performance depends strongly on microstructure and surface quality during hot rolling. The literature shows that current models are either fast but too simple, accurate but too slow, or data driven but not sufficiently connected to physical metallurgy. The proposed hybrid framework aims to bridge this gap by combining mechanistic DRX modeling, machine learning, and oxide scale prediction. The expected contribution of this research is like a more practical framework for real time and prediction and control in HSLA hot rolling. If successful, it could help improve the grain refinement, reduce surface defects, improve mechanical properties, and support more efficient industrial steel production. Thank you.